All right, good stuff.
I got it.
I know that's the last one that I made, so I don't know if I shared it with you, but I realized that like right now. So I know I keep going to do it, and then I can start with other things. Winky. Too late.
We're already rolling. Just gonna edit it.
You should might as well go from here.
What do you mean?
Maybe you could.
Please don't make something better than chapter
Got three
4.
more. Yeah. 34 out of 40. You got 6 points off of that. They were 16, 18, and 19.
So then when we upload, we just redo those ones?
No, no, do all of them. You have to do all of them.
16, okay.
Yeah, so it's the whole.
This is yours.
Yes.
Take my test.
I would though.
I think
Who else do I need to test from? Not you. All right. Gas laws.
good.
Now, to explain what I've given to you is your normal achieving the objectives slideshow, and then my favorite little cartoon strip that I use with my students. So as we start going through the 3 basic gas laws, these are illustrations to help you figure out what stays constant, what change, and what 2 factors change. So you'll put the law and then the formula next to it, so that way you can use it as kind of like a guide. Okay? All right, here we go.
Wait, I have a quick question before we start. So what's the difference between college chem and then intro chem? It's basically the same thing, right?
There's more in this class than the intro.
And if you're transferring, like this one transfers over as general chem anyway, and then the intro one doesn't.
This is for science
So
majors,
do
the
you
other
think
one
we're
is not.
time and not telling me this? Like, for real?
Are you a science major?
Yes.
Then you take this one.
Yeah, but still
I took
you
the other one already, but then I know, but then I realized for bio I actually need this class. I'm like, really? Why did you guys tell me this? I'm like, well, you were a nurse. Yeah, but still. Like, if you saw that was more beneficial, I would have taken that like a while ago.
All right, so here we go.
I hate being pretty.
All right. So, properties of gases. In case you don't remember when we talk about the states of matter, gases expand to completely fill their container. They take the shape of their container. They have a low density, much less than the solid or the liquid state. Gases are compressible, and mixtures of gases are always homogeneous fluids. Okay? The kinetic molecular theory, I like to summarize it as you add heat, you're adding energy to the particles. The particles begin to move faster because they're getting energized. The faster the particles move, the further they're going to spread apart. Okay? So that sums up what happens for the kinetic molecular theory. It's the idea that particles of the gas, even solids and liquids, particles are always moving. Solids are just vibrating in one spot. Okay? Liquids move around, they flow. Gases kind of bounce all around us because they're very energetic. They have a lot of energy. So when the moving gas particles hit another gas particle or the container, they don't stick. They don't just stay put. They bounce off of it. There's elastic collisions. So if you're physics oriented, this is where the physics comes in. Okay. So there's a lot of empty space between the gas particles compared to the size of the particles. Think about when you fill up a balloon. Okay? When you start adding the gas, when you start breathing the air into the balloon, what does the balloon do? It expands. That doesn't mean that there's a gas particle in every single part of that balloon. It just means that the balloon is staying inflated because of the force exerted by the gas particles that are bouncing around inside the balloon. Okay. Which leads us to gas pressure. Pressure is the force exerted per unit area by the gas molecules as they strike the surfaces around them. Just as when a ball exerts a force as when it bounces against a wall, or when the gaseous atom or molecule exerts a force and it collides with the surface. The formula for pressure is force per area. Write this over here. Force per area. know about Newton's laws and equal and opposite force. Something is always applying pressure to move, or if it's not enough force, then it doesn't move. In the case of the gas particles, same thing. Think about what happens if you were to take a balloon and you were to heat it. You put a Bunsen burner underneath the balloon. What are you doing to those particles?
You're making them move faster.
You're making them move faster. So what's going to happen to the energy of the collisions of the gas particles in the balloon? They're going to become greater. So what is it going to do towards the sides of the container then when it hits the container? It's going to expand. It's going to push harder out, and then the balloon at some point, the skin of the balloon isn't going to be able to contain the energy of those gas particles, and what happens to the balloon? Pops.
So they're hot air balloons?
Yeah.
Hot air balloons, it's gas laws. Yes, we'll talk about that. The hot air balloon is because you're changing the temperature of the balloon, and warm air rises, cold air sinks.
Okay.
Because of the density of the gas particles. Think about, and we're not there yet, but I'll go there. So if you think about cold air versus warm air, which one has more actively moving particles? Warm air. Cold air is moving at slower temperatures. Warm air is moving. So the warm air is going to go up. It's less dense. The cold air is more dense. It's down below. So warm air rises, cold air sinks. And when you change the temperature, you're also going to change other factors such as the pressure and the volume. So in a hot air balloon, I believe, when I get this, I believe it's the volume stays constant, the pressure changes. Because you're changing the pressure as you go up. So as you change the temperature, you're going to change, and then the balloon rises, and then the balloon sinks. One day we were out in Lancaster, and we actually were very concerned because we saw hot air balloons out in the sky, and it's not uncommon. I mean, it's very pretty, but we saw the balloon up where like airplanes go. Like it looked like a little speck in the sky moving. We're like, it's supposed to be up that high, but because of the pressure system, they had to go above it to get to smooth sailing, and then we saw them like an hour later start to descend and come back down, and we were like, oh, thank God, like they were really up there. So that's why you'll never catch them in a hot air balloon. I love physics, I love chemistry. It doesn't mean I want to subject my life to that. Same reason why I hate flying. So therefore, pressure is the result of molecular collision. It's the result of the constant movement and the collision with the surfaces around them. The pressure of a gas depends on several factors: the number of gas particles in a given volume, the volume of the container, and the average speed of the gas particles. Right, I'm looking for this. What's that? I took my new marker out. So the total pressure exerted by a gas depends on several factors, including the concentration of gas molecules in the sample. The higher the concentration, the greater the pressure. Right? Again, think about a balloon. As you are adding the air to the balloon, what are you doing to the volume of the container? Increasing it. There's going to reach a point where the inside of the balloon is going to have such a high concentration of gas particles that it can't go anymore. Okay, so it's going to have a greater pressure, and then what happens when it becomes too great? Pop. It bursts. Okay?
The same thing with the bottle cap thing. Maybe you twist the bottle and then too much pressure goes back.
Yes. Diet Coke and Mentos. That's exactly how that works. So, as the volume increases, the concentration of gas molecules decrease. So the number of molecules doesn't change, but since the volume increases, the concentration goes down. All right, so let's use the bottomless soda trick. Well, not trick, but maybe you did it. I've always done it. You shake up the bottle of soda, you put it next to your friend. Hey, can I have a glass of Diet Coke? And then they open it up, and what happens? It explodes all over them, right? Because of the pressure. But if you take a large container and you don't have as much liquid in it, it's not going to have the same force. Okay? So, or exert the same pressure, because you're increasing the volume in which that pressure has to build. When my students did a science experiment of the Diet Coke and Mentos, a lot of students realized that they wanted a bigger blast. They had to use a smaller size bottle. The bigger bottles just were giving a very little burst, and the smaller bottles were giving a larger burst. Okay?
The volume it's more.
It was more concentrated. A lot of them also opened their bottles of bigger soda and drank it, so we're not gonna go into that. That also affected the results. They were thirsty on the bus ride. All right. So the pressure exerted by a gas is dependent on the number of gas particles in a given volume. Take a look at the picture. Tell me what you think. Does this make sense to you without me reading all of that? More particles in the same given area. It's kind of like if they shoved all of us into a subway. And we all had to fit in one subway car versus 5 subway cars. It's going to be a high pressure situation because we're all going to be close together in an area of a given volume.
Have you seen the subways in New York and Japan? How they actually like have people like shoved in there? Like,
Yeah. No, I haven't, but yeah, that's not something that's
no, they
clever.
were so
I don't like New York
compact
at
and
rush
stuff,
hour.
people can't even like fit in there. Yeah, like the security.
Well, isn't India, don't they sleep? Isn't there like you're supposed to lay down or something? The train, yeah, the trains. All right. So what units do we use to describe pressure? The atmospheres, millimeters of mercury, torr, and the bar. For your lab, when we do the molar mass of a gas, we should be using millimeters of mercury or the atmosphere. The conversion factor is that for every 1 atmospheres, it's 760 millimeters of mercury, which is also equal to 760 torr. This is a very important conversion. And by the way, the 760 millimeters of mercury literally comes from the tool that they use to measure the changes in pressure by putting a dish of mercury and an open-ended tube, the barometer, I believe it is. There's also a manometer, so I'm trying to make sure. The manometer is an open-ended. The manometer looks like this. Okay, and then you have your mercury, and then if there's a pressure change, the mercury shifts. The change in the height is the change in the pressure, which is your millimeters of mercury. So it's literally measuring the millimeters of change of mercury. That's where it comes from. If you look anything up on a weather app or weather.com to find out what the barometric pressure is in our area, because we're in America, they have it as inches of mercury. Kind of loses that whole ring to it, doesn't it? Inches of mercury, I like millimeters of mercury, that just makes sense. A barometer is, there's a dish, and then, I'm trying to remember what it looks like. I thought she had a picture of it. And it basically is just a closed-ended tube. And then as the pressure increases on the surface of the dish, the level rises in the tube. So that's the height of the mercury. So pressure, the atmospheric pressure, pressure inside the tube goes up. All right. No. All right. So the physical properties of gases are all interrelated and interdependent. We're talking about temperature, pressure, volume, and the molar amount. If you hold any 2 of these physical properties constant, it's possible to show a relationship between the other 2. These relationships are called the empirical gas laws. All right, first one, Boyle's law. All right, that works. Okay.
Do you want me to adjust it to get the board?
No,
to-
I'm good, because you're not really showing me.
Yeah,
To the viewing audience, disregard. All right. All right. So Boyle's law relates volume and pressure. So what I like to do with my chem students in high school when we have more time, and maybe you did this in a science class, we actually can graph the change in volume in regards to pressure or pressure in regards to volume. So the volume of a sample of gas at a given temperature varies inversely with applied pressure. So if the pressure is doubled, the volume is halved. So Boyle's law as pressure increases, volume increases. So pressure increase, volume increase, temperature is constant.
Which guys are we writing this next to?
Not yet.
Okay.
Yep, we'll go right to that after I get down all three laws. Okay. So it has this relationship, it's inversely proportional as decreases. I knew I said it right, I wrote it wrong. As pressure goes up, volume goes down, and vice versa. No, we're gonna hear is the stomping of your feet. All right, so here we go. Now, because these are empirical gas laws and it all has to do with the change in the system, you're going to have an initial and then you're going to have a change or a final set of calculations because you're comparing, right? If the pressure goes up, well, how do you know if the pressure goes up? You have to have some starting point somewhere. So therefore, if we look at the sample right here, we have an initial pressure of 0.5 atm. We have an initial volume of 1.4. We have a final pressure of 1 atmosphere, and we have a final volume of 0.70 liters. That shows that as the pressure increases, what happens to the volume? Decreases. So you have to have a before and after. You just can't have P1, V1, and nothing else.
Did I edit that out right?
You'd be super mad when I don't know because I don't know how to do it.
I would say if it was opposite, if the volume increases, the pressure decreases.
If the volume increases, the pressure decreases, yes.
I'm just,
Because look, think of all the pressure that's being held on this one, right? So then look over here. The volume, the pressure is less. It's the same idea that we were talking about with the collisions.
okay.
Remember? There's more volume for it to go roam around, so it's going to be less pressure being exerted.
What is that sign in the middle of the V and the?
That means inversely proportional.
Okay, so it looks like
It's a fancy little Greek letter.
Yeah, we use it in physics.
There you go. Physics is the Greek letter alphabet.
Why is physics so hard?
Physics isn't hard, it's fun.
You see all these kids from
Physics,
here.
cool.
So there you go.
It's the way the universe works.
So that's Boyle's law. Ready to move on? Oh, wait. Yes, yes. Okay, here we go. I'm all ready to jump. So, a sample of oxygen gas occupies 38.7 milliliters at 751 millimeters of mercury and 21 degrees Celsius. What is the volume if the pressure changes to 359 millimeters of mercury while the temperature remains constant? Now, here's the thing. Because it's initial and final, you don't necessarily, for this problem, have to convert to liters. Just know that your answer is going to be in milliliters when you solve for it. Whatever you start with is what you're probably going to end up with.
Don't you have to convert the Celsius to Kelvin?
Since it's constant, we don't need to worry about that here. Yep, good question, because there will be one of those empirical gas laws we have to convert. So therefore, what are you given? You're given your initial volume, your initial pressure, and your final pressure. Okay? Just like I've shown you guys to do in the past, make sure that you label everything. V1 equals 38.7 milliliters. P1 equals 751 millimeters of mercury. P2 equals 359 millimeters of mercury. And we don't know what V2 is. But can we solve for V2 using algebra? Absolutely. P1 V1 over P2 equals 751 millimeters of mercury times 38.7 milliliters all over 359 millimeters of mercury. When we solve, we get that our volume is 81.0 milliliters. It's that simple. The hardest problem is trying to figure out which one of the three empirical formulas you're using. It's all worked out on the slides. Can I erase it?
See. Alright.
All right, the next law is Charles's law. Okay. Charles's law relates volume and temperature. So the volume occupied by a sample of gas at constant pressure is directly proportional to the absolute temperature. But he's quiet with this guy.
You missed it. He tried to go that way.
I could have done that. I bet it already has me like just pumping out.
All right, so now we've got Charles's law. So now we've got our volume and our temperature, and they're directly proportional. So it's V1 over T1 equals V2 over T2, and now our pressure is constant. It means that as our volume increases, so does our temperature. Or as our temperature increases, so does our volume.
I think this is so much better than Schroeder though.
So much better than what?
Did I say it?
I told you it wouldn't be too bad.
Am I saying it right?
Stoy?
So,
All right, so in that black bin is dry ice, or sorry, liquid nitrogen. My bad, it would have the same effect. And is shown after being removed. It shrank because the air inside contracts in volume. As the inside warms, the balloon expands to its original size. So decrease in temperature means a decrease in volume, and increase in temperature means an increase in volume. Do the same thing with a balloon at home in a freezer. Put the balloon in the freezer, it's going to contract. Take it out of the freezer, it's going to expand. If you ever go to the store and buy balloons for a party, and you go and you pick them up and it's cold outside, you might actually get outside to go take the balloons to the party and go, what happened to my balloons? Because it's cold in your car. The balloons are going to contract. Once you get them inside, the balloons will expand and float and look all pretty again. Yes, no.
What happens to a balloon when you let go and the balloon to the sky?
It will eventually pop and the birds will eat it and die. So you're not supposed to release balloons anymore. So my environmentally sound students and family know that. I will say that. Okay.
I lost my train of thought.
you lost what?
It's train of thought because I did the whole little the
Side note.
side
To
note.
our viewers.
Just letting y'all know. All right, when you think of it, let me know.
I thought eventually
Sorry about that one.
The atmosphere's pressure would actually like cause the
Well, what happens to the temperature as you go up?
Which goes down.
The temperature goes down, so what's going to happen to the volume of the balloon? So it's going to be the opposite, right? V1 volume and yeah, it's Charles's law. Haha, I was right. Okay, I'm looking at Boyle's law. What's going to happen? No. So as the temperature goes up, the volume is also going to go up. So what's going to happen to the size of the balloon?
so it gets colder out there or hotter?
All right. So sorry. So it gets colder. So as the temperature goes down, the volume is going to also go down. It's going to decrease. But then, depending on how high it goes, there is a level where it begins to heat up again.
So the pressure and volume, so the pressure would have nothing to do with it.
No, pressure would be constant. We were assuming. But if it's all three factors, the pressure is going to also affect it.
Poor bird
So
boy.
you normally don't relate these two.
Ask God, you got it. I'm definitely asking that.
This is, no, you can't relate to two laws because of the constants, the constant changes. And since we're talking about the balloon going up in the atmosphere, the pressure's changing, the volume's changing, and the temperature's all changing. You really can't use it to identify that.
One of those.
For that example.
Okay.
But like hot air balloon staying where the pressure is kind of constant, for these type of balloons where the pressure's constant, then we can use that.
So ever since we're going a bit environmental, like free, like not using like plastic bags instead of paper, how come it wasn't like that like the old generation? You know, I'm not sure. You know where the
I'm not a millennial.
millennial? Isn't it?
beyond the scope of this course.
Wait.
We'll talk it later.
Go ahead.
Yeah.
So, the particles that are in the balloon are slowed down due to the lack of energy from the temperature.
Yes,
Okay, that's all I have.
that's it.
What was your question?
Slow down.
Yeah.
You take away heat, they cool down, the energy level drops. Let's see.
You guys can ask you.
I wish I could take credit for this, this is MIT,
You did this?
not me.
Are they known for their physics?
Yes. My physics professor was a student at MIT. There's music. Figure this out. Thank you.
The balloon looks like you, Mom.
Science is cool, you know. Science is definitely cool.
Alrighty.
Giraffe.
So this is just the graph showing you what happens as temperature increases, the volume is going to increase. The extrapolated lines cannot be measured experimentally because all gases condense into liquids before negative 273.15 degrees Celsius is reached. And this is our absolute zero. All right, so here's Charles's law in action. It doesn't show us the temperature, so that really isn't accurate. Oh, yeah, there it is. Wait, what am I missing? We've got our 100 degree Kelvin and our 200 degree Kelvin. So if our temperature is increasing, what must our volume be doing? Also increasing. All right, so here's our Charles's law example. A balloon at 20 degrees occupies a volume of 346. What will be the volume of the balloon if I place it in the lab freezer, approximately negative 40 degrees Celsius?
It'll come back out the same way.
Okay, yes, it'll eventually warm up to room temperature. Thank you, daughter. All right. So, again, if you notice to your example, they do convert Celsius to Kelvin. So whenever you have a problem where you're gonna have not constant temperature, you have to convert your temperatures to Kelvin.
You add like
273. Okay. So for this one, we have our T1 is 20 degrees Celsius plus 273.15. We have our V1 equals 346 milliliters. We have our T2, which is negative 40 degrees Celsius plus 273.15. And our V2 is what we're trying to find, once it's in the freezer, not after. So we have our V1 over T1 equals V2 over T2. Now, we're solving for our V2, which means that we're gonna bring our T1 over here and multiply both sides by T2, and then we're gonna get T2 times V1 over T1. If that fries your brains, okay, this is the shortcut way that I can show you. You do a cross multiply. V1 T2 equals V2 T1. Now divide both sides by T1. But if you know how to do it algebraically, then you multiply both sides by T2 over 1, T2 over 1, you get the same answer. Yeah, that's, I think some of you just like this way. I don't care, as long as you get the right formula, I'm really thrilled. Okay, so once you get the formula, once you convert to Kelvin, you plug it all in, here we go. So we've got V1 T2 over T1 equals V2. So our V1 is 346 milliliters. Our T2 is, who has the numbers for me? Oh, never mind, I have the numbers. Just ignore me.
Oh, 230.
Yep, 233 Kelvin. Our T1 is 293 Kelvin. When we work it out, it's 276 milliliters.
Do we convert that to liters?
Does not ask for you to do that.
276?
276. Okay. Next law, the combined gas law. See, they skipped one gas law, and that's called the Guy-Lussac's, and that's the law that's responsible for how pressure cookers work. So it's P1, let me look at the ideal gas law real quick. Yes, P1 over T1 would also be part of it. All right, so what is the combined gas law? The combined gas law takes the fact that pressure, volume, and temperature are not constant, but there was that other variable we talked about that hasn't been brought up. The moles, right? We haven't even mentioned the moles at this point. See, you thought we were all done with moles, but we're not. For these two laws, moles are constant. And for the combined gas law, the same is true. The number of moles are constant. Okay? So in the combined gas law, you're going to have 5 givens and 1 unknown. It's all about knowing your units and identifying what you have to get the combined gas law. If you start writing down your givens and you realize that you've got 2 pressures, 2 volumes, and 1 temperature, you're looking at a combined gas law problem. Okay? So the combined gas law takes these. And it's P1 V1 over T1 equals P2 V2 over T2. Now, all right, I'm going to do the whole cross multiplication thing. P1 V1 T2 equals P2 V2 T1. That way it's a little bit easier to solve for 1. Or 2D2. Every time.
I don't like Pikachu. In a good way. He said, I know who was insulting her, you know what I mean?
Oh, I miss that. I used to like playing the Pokemon Go. I was really obsessed with it about 2 summers ago at the college campus. My building was like one of the battlegrounds, the gyms.
That's great.
I would go to the dean's office and a Pikachu or a little Pokemon would be on her desk. Squirtle! And I'd like get them. Somehow I'm still working there. Go figure. All right. So a chemical experiment produces nitrogen gas. The volume of the gas produced is 10.1 milliliters. All right, so let's start writing down what our givens are. See what we got. We got a volume of 10.1 milliliters. We've got an initial temperature of 23 degrees Celsius. We're just going to turn that right into Kelvin just because. And we've got a P1 of 746 millimeters of mercury. So then, what's our other? We have what's going to be the volume of the gas, so we don't know our volume. If we have a temperature of 0 degrees Celsius plus 273.15 Kelvin, and a pressure of 760 millimeters of mercury. Now, can I tell you, I know what Mastering Chem is going to do. For you, those of you watching, if you don't know Mastering Chem, don't stress. Okay? They're going to give you something in torr and something in millimeters of mercury. or give you something in atmospheres and something in millimeters of mercury, so that you have to convert it to the same unit. Just be aware, because I can already see you getting some emails about that one, and you going, right. So,
We'll wait till you-
all right, so how do we set this up?
On the test, we wouldn't have to do that.
I don't know, I didn't look yet.
Alright.
I should know better, I should probably start looking ahead at those. All right, so we've got, you're gonna have P2, V2, nope, we're solving for V2, right?
Wait, I got a question.
Yeah, we're
Yep.
still waiting for you to.
But when it does make us do that, which one do we go to? Do we go to
Whichever
four?
one you feel
No.
comfortable with.
Okay.
Unless it specifies, you do whichever one you like to deal with, because if you have 2 volumes, they're gonna cancel out,
Okay.
okay? All right, so we're gonna do P1, V1, T2 over P2, T1 equals V2. Then we just plug and chug it in. And you should get 9.14 milliliters. Make sure that you have this temperature correctly, which is 296. And this one is 273.15 Kelvin. That's the combined gas law. We good? Okay. Moving on. Avogadro's law.
Here's another one.
There's lots of laws. But if you know the combined gas law, that kind of puts the 3 all into one. Because it's the combined. Then if you have temperature constant, it becomes P1 V1 equals P2 V2. And then if you have like volume constant, it's P1 over T1 over P2 over V2. So if you know the combined gas law, you can derive any of the other ones. All right. Now, if we had Avogadro's law, what do you think we deal with in Avogadro's law?